Standard electrode potential. What is electrode potential? Electrode potential is the tendency of the electrode. Electrode means here metal rod or a metal strip. It has a tendency to lose or gain electrons when it is in contact with solution of its own ions. And when we taken this electrode potential in standard conditions like 1 molar concentration and temperature is of 298 Kelvin and pressure of 1 atmosphere, then this electrode potential becomes standard electrode potential and it will be calculated, it will be measured with respect to standard hydrogen electrode, because hydrogen electrode has electrode reduction potential 0. That's why it is considered as the standard reduction potential, electrode potential. And hence we can calculate the electrode potential of the other electrode by using the standard electrode potential, that is standard hydrogen electrode or normal hydrogen electrode. In case of transition elements in solid state, the stability of the oxidation state can be predicted from ionization enthalpies. But in case of aqueous solution, stability depends upon electrode potentials. And electrode potential further depends upon free energies, enthalpy of sublimation, enthalpy of ionization, and enthalpy of hydration. And the sum of all these three enthalpies gives the total enthalpy on which the electrode potential depends. Enthalpy of sublimation means when a metal is converted into gaseous atom, then this enthalpy is called, the enthalpy required is called enthalpy of sublimation. And when this gaseous atom gets converted into its ion form by providing the ionization enthalpy. Here it is ionization enthalpy. And then the hydration enthalpy to change the metal in gaseous state to metal ion in aqueous state, in solution state. And the sum of all the three enthalpies is the total enthalpy, which is required to convert the solid metal into metal monovalent cation in aqueous solution. And this whole cycle is called the Born-Haber cycle. This whole cycle is called the Born-Haber cycle, according to which we can calculate the total enthalpy. And electrode potential depends upon this total enthalpy, the value of this total enthalpy. It means the electrode potentials are a measure of delta TH, means total enthalpy. And lower the electrode potential, that is more negative the standard reduction potential of the electrode, more stable is the oxidation state of the transition metal in aqueous medium. For example, as in case of zinc, its value is minus 0.76 volts. And in this graph, for first transition series from titanium to chromium, this value becomes less negative, and from chromium to manganese it becomes more negative, and then again increases, and from iron to copper to nickel it becomes more negative in case of nickel, and it becomes more positive in case of copper. Copper shows the unexpected behavior in its series. And again, in case of zinc, it has more negative value of electrode potential, that is of minus 0.76 volts. This minus sign indicates the oxidation of this zinc. It means it get easily oxidized and replace the hydrogen from acids and liberate hydrogen from the acids. But in case of copper, it has positive value, means unexpected behavior in its series. It does not liberate hydrogen gas from the acids. It reacts only with the oxidizing agents like nitric acid, sulfuric acid, which are reduced. Because the positive value for copper, the reason for this is that the sum of enthalpies of sublimation, the sum of enthalpies of sublimation and ionization is not balanced by the hydration enthalpy. It means the value of sublimation plus ionization is more than hydration enthalpy. That's why its electrode potential becomes positive value. Next behavior is of nickel. Nickel shows more negative value because nickel also show more negative value. Here is the configuration. Atomic number is 28, 3D 8, 4s2. In nickel 2 positive state, it has 3d8 electrons. But due to high negative enthalpy of hydration, high negative enthalpy of hydration, its electrode potential becomes more negative. Its electrode potential becomes more negative due to high enthalpies of hydration, more negative value of hydration enthalpy. And in case of manganese and zinc, in case of manganese, here it is manganese and it is zinc, they are also more negative than the expected value. In case of manganese, 2 positive, we have 3d5 configuration, and in case of zinc 2 positive, we have 3d10 electrons, means exactly half filled configuration in manganese 2 positive, and in case of zinc positive it is fully filled d orbitals. And it is more difficult to remove the electron from exactly half filled and fully filled d orbitals. They require more energy to remove the electrons. That's why their electrode potentials become more negative as compared to the other members of this series, and these are more stable in +2 state. Next example is of scandium. Scandium is more stable in +3 state, because in +3 state its atomic number is 21. It means it has 3d1 4s2 configuration. 3d1 4s2 configuration. And in scandium 3 positive, we all the 3 electrons are lost, 2 from 4s and 1 from 3d orbital, and we left with only argon 18 electrons, means stable noble gas configuration. That's why its electrode potential value is very low. This is a reason for low electrode potential value of scandium 3 positive. When the energy is low, means stability is high. That's why scandium 3 positive is more stable in 3 positive state as compared to the 2 positive state. Next is the iron. In case of iron, Fe has electronic configuration of 3d6 4s2. Fe electronic configuration 3d6 4s2, because its atomic number is 26. In +2 state, it has 3d6 configuration, only 6d electrons. But in Fe3 positive, it has 3d5 electrons, means exactly half filled configuration, which is a stable configuration. That's why Fe3 positive is more stable than Fe2 positive state, because of the stability of 3d5 electrons, which is exactly half filled configuration. That's why Fe3 is more stable than the Fe2 state. And the general trend towards the less negative E0 values along the series is due to the general increase in sum of first and second ionization enthalpies. Oxidation states of first transition series. In case of first transition series, the most common oxidation state is +2 and +3. These two oxidation states are most common in the first transition series. This is due to the loss of two ns2 electrons and one electron from the penultimate shell, means n-1d shell. And in the mid of the series, there is higher oxidation states, as in case of when we move from scandium to manganese, means mid of this series, the number of oxidation states increases. For example, of manganese. In case of manganese, there are from +2 to +7 oxidation states. These are due to the participation of both type of electrons, ns and n-1d electrons. Due to both type of electrons, manganese shows variable oxidation states from +2 to +7. Variation of oxidation state is due to the ns and n-1d electrons. And in +2 and +3 oxidation states, means lower oxidation states, these metals form ionic compounds. These transition metals form ionic compounds. And when the oxidation state increases, their ionic character decreases and covalent character increases. For example, as in case of manganese, in permanganate ion, it forms a covalent bond. Here, the oxidation state of manganese is +7. It means when the oxidation state increases, covalent character increases. Tendency to form covalent bonds increases and ionic character decreases. And in lower oxidation states, transition metals form ionic compounds, and in higher oxidation states they form covalent compounds.